Hi, Module 9, Nuclear Power, and we are on a video part 6. Let me get rid of this little record box. Boom. Okay, so hopefully you've taken a pause and you've watched the reactor core videos that show an actual reactor system and one about cleaning the core. And so we can pick up with the light water and boiling water reactor cores. So pressure water reactor cores, PWRs, are kept under pressure so that they are not allowed to boil. And this is a closed loop chamber. So this water never leaves this core. It stays within the core itself. That water is then put in thermal contact, so through the pipe tube with a set of water next to it. This is the water that's allowed to boil. This water is allowed to turn a steam turbine, and that steam turbine then turns a generator. The boiling water is also not allowed to leave the core. It's actually the water that comes in from outside that we pull in, that's the cooling water, that is allowed to come in and cool off the boiling system so that it recondenses and can go through the turbine again. And that's the water that's actually allowed to go up through the steam stacks. So in nuclear power facilities, those big wide stacks on top, those are steam stacks, and they only allow steam through, unlike in fossil fuel plants, which allow carbon dioxide and carbon monoxide. What's going up the stacks is everything that was in the water. So there is radiation in the steam stacks, but that's because there was uranium and thorium in the water that was being boiled as it was put in thermal contact with boiling water. So none of this material is stuff from the core. Nothing is touching the uranium core material. Boiling water reactor cores. So this is the pressure water reactor core, right? And here's my condenser. This is the cool water that's going to cool the system. So closed loop, water never leaves. Closed loop, water never leaves. Condenser, this comes off a river. This is why things like Indian Point, the power plant that's closest to us, it actually slated to close. So this is going to be a very different class when I re-record it in next fall, right? So that's why it's located right on the Hudson. So on the other hand, boiling water reactor cores, or BWRs, are allowed to boil, so it's missing one of those loops. Now, pressure water reactors are considered safer, but they produce a little bit less power for their nuclear breakdown / transition because there's so many stages. As I transfer stages, once again, talking about conservation of energy, every time I'm changing stages to try to transfer this energy from this point to this point to this point to this point on the generator and then out to the grid. When I'm trying to do all this, I'm losing percentages. And so it becomes less and less efficient. So pressure water reactor, less efficient, but considered safer because it has two closed loop systems. Boiling water reactors are more efficient, but they are considered a little less safe because they go straight from boiling water to condensing to cool them off. Boiling water reactors are actually the older module of the two. They came first. These are the systems that were built in the 50s and 60s, and pressure water reactor systems were built in the 70s and are the ones currently being built today. We wouldn't allow a system to be built past this point in time. In this one, the reactor core is allowed to turn that water to steam. The steam is pushed through the turbine. Then it's recondensed, right? And then it's sent right back through the system. And so this is a boiling water reactor system. Power plants, basically after we are done with our fuel, so after we are done with the uranium oxide pellets, there is quite a bit of uranium-235 that can still be utilized. It's just being kept so far away from the other 235, since it's only enriched at 2 or 3%, that it cannot bombard the other particle with a neutron because they are so far apart within the pellet itself. And so one of the things I can do is recycle my uranium. I can take the pellets and I can chop them up and reprocess them, put them through a gas diffusion or a gas centrifuge system and re-enrich them into pellets. This is something that's also not legally allowed in the United States, and it does have some political leaning as to why we don't allow it here. As I mentioned before, there is politics involved, and so therefore we don't allow it here, but it is allowed in many, many countries, like in France and Japan. And so they are allowed to reprocess and recycle their uranium into more uranium-235. And so that's one. And then the next step after it's been reprocessed, if you are allowed to reprocess, once again, in the United States, we just go directly to step 2. We go into long-term storage and then finally disposal, which brings me to the politics of the United States. We actually don't have final disposal in the US. We're still working on that problem as well. So reprocessing, once again, not allowed in the US, but might be. Who knows? Like I said, might be re-recording, and a year or two from now, we might be allowing it. And so I might be explaining something different. I take the fuel rods and I chop up the pellet, and I chop it up with an acid, which disintegrates out the zircon again and allows me to pick up on my uranium oxide, which I turn into uranium hexafluoride, and I put it back through the enrichment process. Some of the material that I will pick up this time will actually be plutonium. That will be under 0.5%. So 0.5% will actually be enriched plutonium, which can also do a radioactive action that can make power and electricity. And so we are allowed to do this. This is called a mixed oxide fuel, or a MOX fuel. There are some reactor cores that are allowed to do MOX fuels. Japan is one of them. They're allowed to load each reactor core with about 20 to 35% of their fuel rods are allowed to be a MOX fuel rod. We do a lot of fuel fabrication, and the facilities that do this reprocessing fabrication exist in Belgium, France, Germany, UK, Russia, and Japan. Once again, just talking about the health factors and the risk and why we don't do it. We cite public health factors, but like I said, many other countries, and we've been doing this since 95, so it's not a new science. It's pretty much just like reprocessing the other materials, which brings me into storage and disposal. So once I pull out a fuel rod, if I'm not going to recycle it, the next stage I need to do is to cool it off. And this is a process called the spent fuel rod pooling. And this is where I put them in water. Now, water is a great barricade. It allows it to do a couple of more chain reactions as it needs to, but not enough to make power, so it can't boil the water. But it keeps the radiation within the water itself. And so I will put it into a storage pool, which will then hold individual reactor cores for a number of years, between 5 and 7 years. And then after 5 to 7 years, I will put it in what's called dry cask storage. Here is the storage facilities. As of right now, there is no nuclear disposal system in the United States, so we don't put them anywhere. They actually stay right on site, but they are left in a sort of semi-mobile on-site form, so that one day, if we come up with a place to dispose of our nuclear spent fuel rods, we will be able to ship that energy there. So it's actually all on site. And you can see this lovely little setup here, which just gives you the metric tons of fuel rods that have been spent that are sitting in-house in various states. So like I said, pool reactor storage, we do it right in a pool. We put in our spent fuel rods, they get dropped down in their assemblages, and they're allowed to cool between 5 and 7 years. After 5 and 7 years, I can then pull them out of my pool. So here's another pool picture. And I can put them into a storage system. The storage system consists of creating a matrix. This is a butamin polymer bromosilicate mixture. And so the matrix starts out with a bromosilicate. Bromosilicate is better known as Pyrex, right? Pyrex glass, so highly able to hold heat. And then it is then cemented on the exterior, and it looks something like that for cementation. And this is my fuel rod assemblage. So now on this, I'm going to pick up with hopefully my last part video talking about fuel cycle, where I'm going to talk about storage disposal.